Hello, you are welcome back. All right, so we are going to begin a new topic. Okay, so this time around, we're going to be looking at the Newton's laws of motion. All right, so now Newton's laws of motion is actually the fundamental law in mechanics. Now, these are the laws that actually establishes relationship between force and motion. Let's start with the Newton's first law. According to Newton's first law, a body continues a body continues to be at rest or in a state of uniform motion. All right, in a state of uniform motion, unless it is being acted upon. It is being acted upon by an external force. So that simply means that the only agent that can actually change the state of a body, whether okay, the body is at rest or in a uniform motion, is an external force. So that is why he referred to as force to be a push or a pull. So the state of rest or motion of a body can be stopped by the application of an external force. I hope that is well understood. So now, Newton first law actually described the principle of inertia. Inertia, all right. So the principle of inertia. So what is inertia? Inertia is the reluctance, okay, of a body to start or even stop a uniform motion. So inertia is always present in any body that is moving. We can actually illustrate the effect of inertia, all right, in a moving car. Let's say this car is moving and you wish to stop the car at this point. Then for this car to stop at this point, then you have to slow down. Why? Because an abrupt stopping of a moving vehicle is not going to be possible. Why? Because the inertia of the movement, all right, that inertia is actually that reluctance or the delay or the unwillingness of an object that is already moving to stop. So invariably, I can't stop this car at this point abruptly if it is moving. In fact, if it is on a high motion, if I stop it, there's no amount of brake I'm going to apply to stop it at this point instantly. Inertia will actually cause it. Why? Because there's going to be a reluctance. All right, so the car will have to, um, slow down, then probably stop at this particular point. That is due to the effect of inertia. All right, and inertia can also be experienced when the car is about to move. There's a form of reluctance to the motion of a car. So invariably, inertia is always in opposite direction to the motion. So please take note of that. So basically, that is Newton's first law. Of course, it describes inertia. So in Newton's first law, there are no there we are not actually considering any formula. All right, in this okay, uh, in this regard. So just describe the principle, right, of inertia. So now we move on to Newton's second law of motion. All right. So according to this law, okay, second law of motion actually states that the change in momentum of a body, change in momentum, okay, is directly proportional to the applied force. The change in momentum of a body is directly proportional to the applied force. So that means the more force you apply to a body, the more momentum it actually changes. Please, not the change in momentum with respect to time. That is the rate. Okay, so let me state that well. The rate of change in momentum. So please pardon me. Rate of change in momentum is change in momentum with respect to time. Okay, so the rate of change in momentum of a body according to Newton, that is change in momentum with respect to time, is proportional to the applied, directly proportional to the applied force. So invariably, if you want to actually increase the rate of change in momentum, or you want to this body to change its momentum, all right, faster, then the force that is applied must increase. Now the question is, what is momentum? Let's start by defining momentum. So momentum in physics is a product of mass and velocity. Mass times velocity. That is momentum. Momentum is a product of mass and velocity. Okay. So how do we now express the change in momentum? So invariably, if we must actually, must have a change in momentum, that means there must be a change in the velocity of that particular body. Since the mass is constant, okay, so the velocity actually changes, and of course we know very well that we use v to represent the final velocity of an object and u to represent the initial velocity. So invariably the change in momentum is going to be mass multiplied by the change in velocity, okay, and the change in velocity is going to be the final velocity minus the initial velocity. So this expression is what we use, okay. We use this expression to represent the change in momentum of a body, m into v minus u. So please take note of that. So let's see how we can now apply it to Newton's law. So according to Newton's law, the second law, so the force applied is proportional, all right? So invariably the constant of proportionality is 1, so I'm not going to bring in any constant. So the applied force according to Newton's is equal to the rate of change in momentum, which of course is a change in momentum, m into v minus u, then divided by time. So anytime you are actually asked to write the expression or the relationship that exists between force and of course momentum, change in momentum, this is it. So of course this expression helps us to calculate the force that is actually acting on a body that causes that the body to change momentum, or right. So we got this particular formula is gotten from Newton's law. So the formula of force is gotten from Newton's second law. Force is equal to change in momentum all over time, and of course you know very well that force is measured in Newton. Okay, so now we can also write it this way from first law. Okay, remember, from first law of motion, which we already treated. All right, you know very well that from first law, v is equal to u plus at. If we make a the subject from first equation of motion, please pardon me, from first equation of motion, acceleration is equal to v minus u all over t, because from first equation of motion we have v is equal to u plus at. So acceleration is equal to change in velocity. If we make acceleration the subject, then divided by time. So now, as you can see, related to what we have here, I have V minus U all over T. So invariably now we can also write force, the formula of force to be equal to mass times acceleration. Okay, so in terms of rate of change in momentum, this is the formula. And in terms of acceleration, this is the formula. So let me call this 1, of course, so let this be 2. So depending on what is actually given or the parameters, we can actually use the force is equal to mass times acceleration, or we can use force is equal to change in momentum then divided by time. So please take note of this. All right. Now let's proceed with more derivation from Newton's second law. Okay. So already we know that from Newton's second law, force is equal to the change in momentum all over time. So I'm going to actually cross multiply. If I cross multiply, I'm going to have force multiplied by time is equal to change in momentum. So the product of force and time is equal to the change in momentum. All right. The product of force and time is what is known as impulse. The product of force and the time, all right, on a body is what is known as the impulse. So invariably, impulse on a body is equal to the change in momentum. So anytime you are being asked to calculate impulse on a body, that is a body that is actually being acted upon by a force, and of course at a particular time, such is known as at instantaneous force, then that is what we are also looking at in that regard is change in momentum. Okay, please follow me. Okay. Okay, so all right, I think it is really very important for us to actually understand this basic uh, principle in Newton's second law. Okay, so please take note. Impulse is equal to change in momentum. So invariably, if you are calculating impulse, all right, if you're asked to calculate impulse, you are also asked, you are also required to calculate. Of course, that is impulse is equal to change in momentum, so they are equal. So invariably, anytime you're calculating impulse, then it's this you use the same formula, all right, to calculate of change in momentum. Okay, so that is it for this video. So in the next video, we're going to look at the application of this formula. Okay, so let's continue in the next video. So see you in the next video. Thank you very much.